Even when we're working on engine components that are over 70 years old and probably should be scrap iron, we're always looking to try new things and improve our process. This is the 255 Mercury Flathead that we tore down a few months back after our customer let it sit for decades. In the previous videos, we've already bored and decked the block and attempted a risky crack repair. So now we need to finish machining the new valve seats and get one step closer to seeing this engine run for the first time in over 50 years. Flathead Ford engines have a somewhat unique valve guide design, being that the guide itself is a slip fit and removable from the block, as opposed to other more common designs with permanently installed press fit valve guides. This presents us with a challenge as we do not have a rigid valve guide to use when machining our valve seat. We use a 34.5 valve seat machine which utilizes live pilot valve seat tooling and a triple airfloat centering system. But without a rigid valve guide in the block, we lack the ability to center up on our valve seat, let alone the ability to successfully machine the seat without chatter resulting from the lack of support on the pilot side of the tooling. To solve this problem, we're going to attempt to machine a mock valve guide to use during our valve seat machining. The mock guide will be long enough to extend as a slip fit into the lifter bore of the block to maximize true alignment between the valve lifters and the valves, while also having a slight taper on the OD of the top side in order to wedge solid into place in the valve guide bore. It will also need to feature a 3/8 inch inner diameter hole for our valve guide pilot to stabilize our valve seat tooling. After measuring the guide bores in the block and discovering a wider range of diameter than we expected, we decided to pull our OD measurements off of our old Sioux brand dead pilot, which we've used in the past on these blocks. We know that it wedges in tight to the guide bores, but we always felt it could be improved if it also aligned with the lifter bores like the tool that we're trying to make. Knowing that the valve lifters are a slip fit into the lifter bores, we also measured a lifter to get our dimension for the lower OD of our mock guide. With these numbers and a quick sketch in Fusion 360, we had a plan. We had a section of 1.25" round stock low carbon steel on hand, so I got the horizontal bandsaw out and cut off a long enough section for our part plus extra to chuck in the lathe. For the record, I'm nearly completely self-taught on the lathe, excluding some very brief instruction on a manual lathe when I was at the University of Colorado studying mechanical engineering. I want to hear your criticism, but let's try to keep it a little bit constructive so that I can learn and improve for future projects. For the first operation in the lathe, I simply face off the jagged saw cut edge of the part. For the next operation, I pulled the workpiece out of the chuck approximately 7 inches since our final part is in the realm of 6 inches long and I want to leave some tool clearance to the chuck. My hope was that I would be able to get a nice straight hole drilled in the end of the workpiece, set up the live center to support the workpiece, and turn the OD in the same setup to maximize our chances of having the ID and the OD of the mock guide concentric and aligned to each other. I started with a center drill going deep enough to leave a 60-degree chamfer after drilling the ID. Next, I used a U-size letter drill to drill a little bit over 2 inches deep. My hope was that by using a U-drill at 0.368 inches diameter, it would leave me some extra material to hone out for a nice tight slip fit to our sturdy 3/8 valve guide pilot. I also used a pecking cycle on the machine in the hope that it would give me the best chance of the drill staying concentric and aligned. For turning the OD profile, I had drawn the design in the shape creator of the Haas visual programming system and then was attempting to use an irregular path cycle to turn the part, which I have used in the past with success. Essentially, the lathe follows the drawn path over and over again in set increments, starting at a larger diameter than the stock and working towards the finished part. my bar was not true. Between cuts, I would measure the part and then adjust my tool offsets in an effort to hit our OD dimension on the money. But to be honest, I don't know what happened, and it took a deeper cut than I expected. Hear what the happened. I don't know what the it did. After finally deciding to stop the cut halfway through, check everything out, and start again, we were back on track. Okay, so it should not cut this time around. Except maybe where it's foobar. Apparently that was our finish pass. Apparently that was our finish pass. I think it's a little big over here. We hit our OD dead nuts on the lifter bore size, but the taper side came out slightly large. Maybe that has something to do with a $50 Amazon Live Center operating well above its rated RPM range. I could run that a finish pass again and let it just skim over it. All that did was ruin the surface finish. Now we're actually pretty close to where I wanted to be. Nevertheless, we put the part back into the saw and cut off the excess stock, and then cleaned that up on the belt sander. With the diameter slightly large, we figured that we can always come back later and massage it with a polishing belt until we had a nice good fit in the block. At this point, we noticed that the hole we had drilled came out larger than expected, already being a loose fit to our guide pilot without any extra honing. It was also clear that the end of the drill had indeed wandered, which, again, we sort of expected. Does anyone have recommendations on tooling and processes for drilling deep holes like this successfully? Obviously, with our ID misaligned from our OD, the goal of the mock guide providing better alignment for machining the valve seat isn't going to happen. So we went to plan B, bore a straight hole to install a valve guide inside of the mock guide. Our original design featured a slot to allow any chips to fall through the ID of the mock guide, so before boring the ID, we went ahead and cut that slot on the mill in the hopes that it would help us when we're boring this hole. Next, we chucked the part back in the lathe and drilled the hole out to a 1/2 inch diameter, since our smallest boring bar requires a minimum hole size of 0.480 inches to start with. This is a 3/8 inch diameter steel shank boring bar, and unfortunately we're looking in the realm of over 2 inches of stick out, thus meaning less rigidity, thus meaning chatter. I had started at the recommended feeds and speeds for the insert being used before slowing things down quite a bit for the next few cuts. While it sounded better, it still didn't come out perfect, but I figured we came out in the realm of a loose press fit for the valve guide anyway. And I'll be honest, I used my highly accurate digital calipers to measure the hole as opposed to setting up one of our bore gauges that we typically would use in the shop. We decided to use the torch to heat up the mock guide in the hopes that it would expand and gain us some ease in installing the manufactured valve guide. But it didn't go in perfect, so I had to move over to the press. This thing was pressing tough, and right about here, it clicked. Crap, I forgot to use press fit lube. And that, folks, is why you never go in dry. So I started over, but I did not get very far.
Dude.
Remember that $50 Live Center I mentioned? Don't worry, it's in the scrap now, along with all of my Flathead Ford mock valve guide hopes and dreams. I guess sometimes you try new things, and sometimes you get in a little bit over your head. But it's always good to have the tried and true methods to fall back on. The tried and true method in this case is to take one of the slip fit valve guides for this block and do a slight knurl on the OD in an effort to tighten up the slip fit and take out any slop. Being a slip fit, we do still have to support the bottom of the guide to keep it in place during machining, so we have the cam and lifters installed, and this socket is a perfect length to support the guide. To set up our valve seat cutter, we have a special tool that we can use to transfer a measurement from the face of our new SBI valve to our cutter. The valve seat profile will essentially be a 60 thousandths wide 45-degree seat with a sliver of top and bottom angles. The seat should contact the face of the valve roughly centered or slightly biased to the outside diameter. Although we'll be using the newer style adjustable valve lifters, we can still use a feeler gauge with a non-adjustable lifter to get an idea of how deep our seat should be cut to be similar to what it would have been when it left the factory in the 1950s. Without adjustable valve lifters, your option would be to decrease the lash by cutting the valve seat deeper or grinding the valve face thinner, or increase the lash by grinding the tip of the valve. Again, it's not as big of a concern for us, but it's still good to know that we're in the right ballpark for our depth. In situations where we lack a perfect valve guide, it requires slightly more operator finesse on the SERDI to avoid chatter. But another thing that helps is to keep the contact area of the cutter as small as possible. In this case, the newly installed valve seat inserts are slightly small on the ID, and by the time we got to our full seat depth, the chatter is starting to arise. As such, we can go in with a cutter on the ID to open up the valve seat and blend it into the port, similar to how this block would have looked when it was brand new. We can also use the SERDI's continuous spindle speed variation feature to vary the RPM of the cutter as we do our machining, thus helping to break up any harmonics that arise and further prevent chatter. On an engine with a bit more permanent valve guide design, we would typically go through and use the rough cutter on every valve seat, then come back and use the finish cutter on every valve seat. But in this case, it was kind of a toss-up time-wise, since we do have to move the valve guide between each valve seat as well, which does take time. I decided the most efficient method would be to install the knurled guide in a guide board, use the rough cutter to open up the seat ID, then change over to the finish cutter and finish out our valve seat. Before moving the knurled guide to the next guide bore and repeat. All in all, it took us roughly 3 to 4 minutes per valve seat, putting our total valve seat machining time on this block in the realm of 45 minutes to an hour, not including any of the setup time involved, nor the time to install the seat inserts originally, which was done prior to this video. We already knew that the tried and true method would work, hence tried and true, and it actually works pretty dang well with some finesse, but we'd still like to try and improve things down the road with a mock guide. If nothing else, for our own satisfaction of knowing that we can do it better. So drop your hints for a young guy teaching himself the world of CNC turning, and be sure to like and subscribe to support the channel as we work towards bringing this 255 Mercury Flathead back to life. Thanks for watching.